Hello, it's James from XRobots.co.uk. This is part 11 of Project Ultron, which is going to be this life-size Ultron torso, which is going to be fully robotic, because Ultron's not a costume, and it's going to be driven partly by a motion capture suit that I've built, and you can see this in the early episodes, and partly by its own AI. So have a look at part 1 and some of the early R&D episodes to see how that's going to work. So last time I got as far as putting these shoulders on, which lift up like this to give an increased leverage angle, and they also rotate around. And there's some reasons for that in the early episodes where I did a little test robot arm driven by the Euler angles that came directly out of the motion capture sensors. So today we're going to try and actually make some of this motorized at least. I've got some sort of ab actuators that can shift this platform around, and now we need to put some in that move the arms around so we can do some good motions with it. So let's have a closer look at some of those challenges. We have two axes I need to motorise. One of those is moving like this, and the other one is of course moving the arms upwards, and then there's a third rotation on the biceps turning them this way. And the reasons for that is in part 3 of this series. The shoulder hubs I've got here also have some squashy bits in the middle, and those are going to have force sensitive resistors inserted so I can get some feedback on the force. And I did some testing on series elastic actuators in part 4, so check out that video. The other ones are going to have those still built into them. So the actuators that pull this backwards and forwards are still going to have that series elastic component built in, but there's hardly any force pushing these. There's really not too much effort. They just coast round. Doesn't really matter what I hang on these, they coast round on bearings. So that's no problem really to build quite a small actuator that's going to fit in the front basically, in the chest to pull those backwards and forwards, and we're going to do that hopefully in this episode as well. The challenge I've got is moving the arms out because there's quite a lot of leverage about here, and that's one of the reasons I've made these really chunky and built those really big force sensors in there, is that actually already to lift this is actually quite a lot of effort. So we need some fairly hefty actuators. Now I was going to go and build some out of 3D prints, but then I decided that actually this is really critical, especially with the arm hung on it, and if this doesn't work it's going to be stupid. So I thought I'd actually use some metal. So let's see what I'm going to use for those. Yes, I'm going to use actual metal actuators. I got these off eBay. These are apparently B grade, which are a bit cheaper than they normally are, and these are an 8-inch stroke length, which is about 200mm, and they're incredibly tough. So obviously they've got lead screws in them and everything. They've got end switches as well. There's no position feedback, but that's something I can take care of later. So I'm just going to stick those on some power. I've got a pair here, but I'll be using a single 11.1 volt LiPo. These have got end switches as well. So if I go the wrong way, nothing happens. If I extend this outwards, there we go. These are the high speed ones apparently, which are about 30mm a second. To push that arm up, it needs to do about 2.5 times that, so it's going to take about 2.5 seconds to extend all the way up. This is more reach than I need, which I'll discuss shortly. So, and obviously this goes back down again, and they're rated at 20 kilograms, which is quite a bit. It's just under 50 pounds, I think. So that's more than enough, and it will be when the 3D printed arm is hung on. I'm not sure if I can stick this wire in, but I don't think I can physically stop that actually. So that's more than enough force, and hopefully this is going to be a good basis to build those arms on so they run smoothly without any issues. So what was going to happen was basically I was going to attach actuators to the bottom of this plate to push up on these each side, and the reason for that was that these are also actuators which shift that plate around and backwards and forwards. So that made a lot of sense, but now there's not actually space of course to get these things in, and I've got one here, so these are quite gigantic. So the plan in fact is going to be to brace them off the bottom of this so they fit in here like so, and then they fit in there quite nicely. So I've actually got a stroke length I mentioned is 200mm, which is about 8 inches. I need 80mm here, and these are capable of moving 100, so that gives me 180, and I've got a stroke length of 200. So in fact what I can do, if I want to move this plate around, is either move the arm with it, or I can keep the arm stationary, which is going to be quite interesting. So obviously if I want to raise the whole side up, I'll push both actuators up, or I can keep this one still and just move the arms, or I can move just this plate around and keep the arms in one position. So I think the result of that is, of course, I can move the arms independently and that's fine, but if I keep the arms still and try and move the body, I think that's going to be quite a weird kind of effect like this. Or something. I don't think I can actually do it as a human. But anyway, let's see what happens. The other effect, of course, it has is to stabilise this top. So at the moment there's quite a lot of side-to-side wobble in this, but with this V shape on each side made of these two metal actuators, that should actually take out quite a lot of that wobble, because it's going to make a rigid metal triangle, so that's going to be quite useful as well. I've made some brackets for those actuators, so we've got these on top, which allow me to stick those onto the bottom of the shoulder assembly, and then I've got these parts which go onto the bottom of the actuator, and they make a thing like this, which allows the actuator to hinge on this point, and this fits in the base of Ultron so it can rotate. So that fits on there just like that. And that allows rotation that way, and also rotation this way, so that it can rotate round as the arm does. So I need to assemble the other one onto this actuator, and then we can get them fitted. Those brackets are fitted in at the bottom, so now my arm moves. It obviously can't move past these actuators, but that was going to be an issue anyway wherever I put the actuator. So, but there's quite a range of motion. It's at least as good as my test arm. So there we go, let's have a look at it from another angle. So obviously the arms can move like this, or they can move like this. I'm considering putting this whole thing on a turntable so it can stretch one arm forward further, but that'll come later. But for now this is enough range of motion, since the biceps can actually rotate at the bottom, so it can bend its elbow and bring its arm round forwards. So I don't think that's going to be too much of an issue, and these actuators are more than strong enough now to lift this assembly up, as well as being able to skew this plate with the other two actuators, so I should be able to get enough reach. And now I need to build an actuator to move those shoulders backwards and forwards. So in the green part here, which is the main hinge part, I left these anchor holes so we can have a lever that pulls backwards and forwards towards and back and forward towards the chest. So there's plenty of space in the chest cavity there. The front panels I've got, which haven't been printed yet, are far too thick really. But even with them, there is quite a large space there for two actuators, obviously considering that the shoulders move into some of that space. So I think those look a bit like some sort of rotary thing with a lever on the bottom that pulls backwards and forwards to the green part, and those will be some geared motors and so on, acting a bit like servos with position feedback and also force feedback. So I need to again build those series elastic actuators into them. So the same as I did with the shoulder hub, so I can measure the force either being back driven or if they crash into something. Looking at that in more detail, I've broken this into several sections, so it's all going to be driven by a gear. I'm not sure if that's directly off the motor, but I've made one that will eventually fit on the motor, and that's a 6mm shaft with a captive nut in there. There may be another gearing stage in between. But basically this whole thing is concentric, so it spins on the same axis, but it's in two parts. The bottom one has a hole I can drive the lever off, and the top one essentially rotates a little bit inside the bottom one. So I just come and get this and move it up so we can see inside. You can see we've got two halves that kind of interlock, and that allows a small amount of movement. And again, I've got those cavities in there, the same as I had with the shoulders, so I can insert some blocks that I can tune up by printing them in different materials, and I can insert those series elastic actuators in as well as stoppers, so then I can measure how much force is being applied as one of these rotates against the other. And of course the pink part is rotated by the gearing, and the yellow part is then pushed through the series elastic part to actually drive that output joint. So I need to get these printed and assembled. There's room for bearings all the way through, so they should move pretty freely. Then we can start thinking about whether if the gear on the motor turns them too fast or not fast enough. Right, here they are. So we've got the two sections as I showed before with bearings top and bottom, so they're both able to turn, and they will turn about a common shaft which will be mounted on those other mounts, like so, although in fact they only do a 180, and there's a slight bit of movement between them, which is where the series elastic part comes. And if that's not enough, then I'll have to basically file these things down so that they can rotate some more, and that is where my series elastic actuators get inserted. I need to buy some more of those. I've still only got a pair. Those will go down these slots, and they will then be squashed by blocks of rubber against these things so we can measure the load. So that is the output shaft which comes out of the bottom, and that will then push as this turns. So with this on top turning, being driven here by the gear that fits on top, then we can measure the load between the two stages, and this is the output stage. So I've put some little gears on my motors. These are 300 RPM gearhead motors. There is a captive nut in there. So you can just see a nut in a slot, and I've made a grub screw with a piece of bolt with the end chopped off and a slot cut in it so I can screw it in. So I've got two of those. So initially I'll try driving them straight like this, but we might need another gearing stage again to make them slow enough. But I'll put these together, and then we'll power up one of these motors and see how fast it goes. I've just put this in a vise so I can test this. Obviously, two halves can move against each other a bit, but that doesn't matter, and they slot into each other. So I've now got my gearing installed, and I've just got a battery and 11.1 volt LiPo on the motor, and that's a 300 RPM motor. Now this is an 8-tooth gear, and this is a 36-tooth gear, which means I've got a 1 to 4.5 gear reduction ratio, so this will go 4.5 times slower. So at 300 RPM, this should do 66 RPM, so that's roughly 1 revolution a second, which means to do a 180 is only half a second, and that's what we need to push the arm backwards and forwards. In fact, I think it's slightly slower than that, but let's try it. So if I just hold this here for now. That doesn't seem terribly fast, so if I try and go from where the slots are and do a 180, yeah, it's pretty quick, and that's going to be moving the arm entirely from back to the forward position. So in the middle it's only doing quarter of a turn to the outside. So I think I need this to go much slower, probably at least another 4 to 1 or 2 to 1 or at least between these two gears. So we need to work out how to mount another gear in there. And that looks like this. So if we just get rid of those chest plates, I've actually mounted these closer together because I realised that the arm mechanisms of course have to swing round and move up, and they will crash into them if I had them where I had to start with. So I've put this whole assembly in. I've also put the intermediate gear in, which is this gear here. So that one binds on the big gear, and the big gear then binds on the small gear. So that gives me another gearing stage where this small gear has to go around many teeth on the larger gear, and I've still got my small gear to the big gear. So that gives me roughly another 2 to 1 just over to make those run slower with more torque. And basically the main part here is these two brackets, top and bottom, which are these two green brackets. Those were attached to screw holes which I left in the frame there for just such an eventuality, which you can see just here and here, and I've left the equivalent screw holes in the parts to screw those in, and I've left a means of getting the screws in as well by making these much bigger holes. Now they're going to be solvent welded on as well, but initially they'll just be screwed into place for fitting. Those of course hold the studding that the actuators essentially run on, so that's 8mm studding, and they'll also hold the motors. So the small gears here are for the motors themselves, and I need to work out how to mount those. I need to stick some extra mounts on top for the motors, and the output shafts are in fact off centre, so they'll happily sit in that position. So hopefully that'll all run fine. Then of course the lever comes off the bottom of these. It goes around the outside and pivots onto the green piece, and that still needs to be made once these run okay. So that should give me more than enough range of movement and nothing crashes into anything. So the brackets are quite interesting. One of them, the bottom one's fairly easy to print. I've turned it upside down to print it flat on the bed. The other one has this overhang which is needed to run the studding down for the intermediate gears. So that's going to be needed to be printed with support material. So here it is in Slicer. So this is the actual G-code, the toolpath for the printer, so we can see that we get these green things being built up, which it then prints the actual print on, and there's a thing called interface layers there, which are these 3 layers, which are weaker layers that are easier to separate. I'm going to reduce that to 1, because I think once this starts printing and the plastic shrinks slightly as it cools, then it will warp and pull off. So I'm going to use less interface layers so I can still get it off, but it's nice and strong. So we'll get those printed and hopefully it'll all fit together. Those printed fine, so these things came out really well. They had some support material which just came off really easily with that one interface layer, and they're pretty clean. There's a bit of mess on the bottom, but the parts didn't really warp at all, so that's really good. So that's the top brackets, and the intermediate gears I've printed as well. So they are going to fit just on 6mm studding, which they seem to rotate. They don't go anywhere near that fast, of course. The thing's only doing a 180, so they will mount onto these little arms, like so. And my motor, as I say, has an offset gear, so that can then go down like that and be mounted so it meshes with the gear there. And I need to make those mounts for the motors and get that spacing exactly right. And then hopefully the rest of the things should all run on the shafts that go between these 2 brackets, and everything should be great. So this is one of them. I've attached that second sort of offset piece, which is the lever that pushes the arm, and I've got a captive nut at the top, and at the bottom I've used a nut and a shake-proof washer, so that seems to be fine. So we need to mount these onto the actual torso, see how well all these gears mesh together. Okay, so those are mounted. They do mesh properly, which is okay. There's a little bit of backlash because the gears are a bit far apart, so ideally I'd want to reprint this bracket and put them a bit closer. But for now I think it's going to be okay. And this motor needs its bracket, but it helpfully sits in there. So if I hold it in place, and don't run it past its end stop, let's just see where I am. Right, like that. That's better, so we can see that turns much slower now. If I can mount this motor properly, the gears won't rattle so much. But we should have much more torque as well. There we go, so that seems a much more satisfactory speed out of the main output. I've made some motor mounts, and those are printed in 2 halves, which are flat on the bed, and they screw together to make this. And that means I can solvent weld the bottom down to that top plate on the robot, and then I can change the top if I need to make it more or less grippy, so the motor will of course fit in like this, and this ring will be tightened up. Now I could make one with a sort of nut and bolt in, or I could put a Jubilee clip round. For now it's a cable tie, and if that doesn't grip well enough then I can always change the top for one that's more grippy, and that of course means the motor will overhang the side and mesh on that intermediate gear. Right, the motors are fitted. I've also remade this bracket, so I've got the other one here. What I did was bring these holes slightly further forward, so these gears mesh much better now. So there's hardly any play in those. There's only a little bit, and I can actually see the actual motor gear turning on the output of the motor there, which gives me a tiny amount of backlash and movement in the arms. And I've still got that series elastic part there, which moves much further, so I can get my full sensitive resistors in to measure the motion. So that looks pretty good, and now I've got quite a lot of torque. I do need to put some position feedback on this, and that's probably going to go right on the ends of these, on the actual output, on the motion, or on the bottom of these. So I'll just attach pots in line with these that do the feedback with the bridge that comes round. But I'm going to do that when I actually deal with the motion control. I'm just going to stick some power on one of these and we can see how fast it goes. And bear in mind this is full speed, it will be PWM controlled and PID controlled. So it's a bit jerky when I just turn the motor on and off. But top speed, of course it will go slower, is roughly that. So that appears to work pretty well. Right, I'm just going to do some tests on the range of motion now. So I'm just going to put this linear actuator up when I've got a battery and the cable just here. So we're going to move it up as far as it will go with the main plate and the ab actuators fixed, which is quite some distance till it crashes. So that puts the arm out, well actually almost horizontal there, and it's attached to these brackets, but it's so it's about that angle. But then I can put the abs up. And now that's up, we can put the arm up even further. Yeah, that's about it there. So it does put the arm almost out like this, which is quite good. And I can in fact bring this side down further, which I haven't done. So I can bring that ab actuator right down and that will pivot it slightly even more, maybe give me even more reach. I'm pretty happy with the range of motion that we've got there. Obviously these pieces are seated in NinjaFlex blocks, so they will be attached to the static part at the bottom of these actuators, so they will move sideways with everything to keep that torso upright. The only piece that doesn't fit right now is this, which was in here. That's really not going to work anymore, so I need to rethink that part, but I never fixed it on because I knew weird things were going to happen. So, pretty happy with the actuators. Obviously I've got the series elastic part in every one of these hubs. So not only can it move and sense its position, but it can sense force feedback when it's crashed into things, but only if it wants to based on its own AI. So have a look at the earlier episodes in the series elastic actuator testing video to find out more about that and more about the motion capture in the early parts 2 and 3 as well. That's all I'm going to do for this episode. Next time I think I'm going to work more on the cosmetics and design some of those body pieces, try and get the surface detail on and get some of those attached and work out if those need to move with the shoulders as well and how the spine works. So don't forget to subscribe to my channel to check out more updates on this project and other projects, and also check out the social media links in the description to this video. That's all for now.